Now, before we jump into examples, I want to make sure that we understand, first of all, what is the definition of an equation? And then, what does it mean to solve an equation? So here's a definition for us. An equation is a statement that two expressions are equivalent. The word equivalent means equal value. Let me give us some examples of some expressions. An expression, I'm just going to make these up as I go, can be something like 2 times x minus 3. That's an expression. Or, I don't know, just the number 5. That's an expression. Or 5 plus z. That's an expression. Or, x, y squared minus z. These are just expressions, okay? It could be just a number, it could be just a variable, or a sum or difference of numbers and variables. These are expressions. Now, in order for it, none of these are equations. None of them are equations. They're just expressions. In order for you to have an equation, you would need two expressions, and you would need to show that they are equivalent or equal value. And most of the time in mathematics, we use the equal sign to denote equivalence. Let me show you some examples of an equation now. An equation can be something like 2x minus y is equal to 8. That's an equation in two variables. Let me show you another one, 5x squared, and I'm making these up as I go, plus x minus 3 is equal to 0. That's a quadratic equation in the variable x. These are equations because you have an expression on the left set equal to an expression on the right. So this expression, this equation is a statement that's saying that this expression is equivalent to this expression. Here you're saying this expression is equivalent to this expression, which is just 0. Let me give us just a couple more here. 2 to the power x minus 5 is equal to 13. This is an equation. The expression on the left is equivalent to the expression on the right. So what you and I are going to do in this course is we're going to solve a variety of equations, a lot of different kinds of equations. In this particular section, we're going to focus on linear equations. So I'm going to define for us what a linear equation is in just a minute, but we are solving these kind of equations. Now, what does it mean to solve an equation? So to solve an equation means to find the value of the variable, or variables if there's more than one variable, that satisfies the equation. What that means is find the value of the variable or variables that make the statement true. So that's what you and I want to find. The equations in this section are linear equations, so they're going to be in just one variable. And so you want to find the value of that variable that makes that statement a true statement. Let's look at our first example. Solve the equation 5 times 4x minus 3 is equal to 14x plus 9 minus 2x. Now, before we jump in and start solving this equation, the first thing I want to highlight is the fact that this is an equation. I know they're calling it an equation, but it's an equation because this expression on the left is being set equal to this expression on the right. Therefore, this is an equation, and this equation will be satisfied for a particular value of x. In other words, there's a number out there. Hopefully, there's a number out there such that when we plug it in for x and for the variable, all of these x's, by the way, when we plug that value in for x, it makes this expression on the left the same value as the expression on the right. Okay? Let's find that value of x. Hey, one more thing about equivalence. This equal sign means equal. Just because things are equal doesn't mean that they have to look the same. This expression obviously looks different than the expression on the right. So things don't have to be structured the same way in order for them to have the same value. I'll give you an example. What's the value of a dollar bill? $1. What's the value of 4 quarters? $1. So although 4 quarters and a dollar bill are different are composed differently, they're structured differently, they have the same value. So this expression, although it's different than the expression on the right, what we're trying to say here is that they are equivalent, which means they have the same value for a particular value of x. Okay, enough talking here. Let me walk you through solving this. Now, the operation between the 5 and this expression 4x minus 3 is multiplication. We know that because these parentheses here are a grouping symbol, but they're also an operation, meaning multiplication. So what we're going to do is we're going to distribute the 5. Now, every term inside the parentheses must be multiplied by the 5. On the right-hand side, simultaneously, I'm going to combine like terms. Now, this is very important. Like terms are terms that have the same variable and the same power on that variable. Here, let's step away from the equation just for a second. Like terms are terms that have identical variable parts. What do I mean by that? Well, there are two different types of terms. There's a constant term, which is just a number, like the number 5, for example. It has no variable. That's why it's called a constant term. The other kind of term is a variable term. A variable term is just a term that has a variable. So this is an example of a variable term. Okay, so you got constant terms and variable terms. All right, in order for two terms to be like terms, they have to have identical variable parts. Now, a little more vocabulary for us. This variable term has two parts to it. The variable part, which is x squared, that's the variable part, and then the numerical part, which is -3, also called the coefficient. So we have the coefficient, -3, and we have the variable part, which is x squared. So let me go back to like terms. These two terms, 14x and -2x, by the way, the sign in front of the term belongs to the term. So you would say the coefficient here is -2. But anyway, these two terms are like terms because their variable parts are identical. You got x to the first power. That one up here is invisible, but it's there. And you have -2 times x to the first power. So because their variable parts are identical, you can combine them. And the way you combine them is by just adding or subtracting their coefficients. So 14 minus 2. 14 minus 2 is just 12. And so when you combine these two, you're going to get 12x. You keep the common part. You keep the variable part the same. So over here on the right, 14x minus 12x is just 12x. Bring down the plus 9, okay? On the left-hand side, 5 times 4x is 20x, and then 5 times -3 is -15. So you're going to have 20x minus 15. Okay, there are no like terms on the left. These are not like terms because this is a variable term and this is a constant. Same thing happening on the right. Variable term and a constant. So there's no more combining like terms. Now, in order to solve this equation for x, you want to isolate your variable. The reason why you want to isolate is because this is a linear equation, okay? Which means that the power on x is only 1, right? This is x to the first power, x to the first power. So what you want to do is isolate x. In other words, you want to get x all by itself on one side of the equation. Right now you have 20 x's on the left and 12 x's on the right. You want all of those variables to be on one side. And it does not matter which side you collect your variables. You can collect them on the left or on the right. For me, I prefer to collect my variables on the side that has more of them. The left-hand side has more x's, so I will move this 12x to the left. The way you move any kind of term across the equal sign over to the other side is by using the inverse operation or the opposite operation. This 12x is positive, so the opposite operation will be subtraction. So I'm going to subtract 12x from both sides. As long as you do the same exact thing to both sides, you are good, okay? So 12x minus 12x is 0. I'll just cross that out, so that all you're left with on the right side is 9. 0 plus 9, or just 9. On the left-hand side, though, you have 20x minus 12x, which we know to be 8x. Bring down the minus 15. Now all of your variables are on the left side. If you're going to isolate the variable, that means you want the variable by itself. In other words, this constant term has to go to the other side. The only way you're going to get the negative 15 to go to the other side is by using the opposite or inverse operation. The opposite of subtraction is addition. So I'm going to add 15 to both sides. We know that negative 15 plus 15 is 0. So I'll just cross that out. And what we have now is 8x on the left, and on the right, 9 plus 15, which is 24. Now the operation that is between 8 and x is multiplication. This is 8 times x. There's no operation symbol, but when a number is right next to a variable, it's implied to be multiplication. So because this is multiplication, the opposite of multiplication is division. So I'm going to divide both sides by 8. We know that 8 divided by 8 is 1, so that goes away. All you're left with is 1x, or just x. And 24 divided by 8 is 3. This is the one and only solution that satisfies the equation. What does that mean? If you take the number 3 and you plug it in for all of these x's, you're going to get a true statement. Let me show you that now. Here's the original equation, you guys. And what I'm going to do now is I'm going to plug in the number 3, which is our proposed solution, in for all of the variables. So it'll look like this. 5 times 4 times 3, then minus 3, is equal to, supposedly equal to, 14 times 3 plus 9 minus 2 times 3. So notice that I replaced all of my variables with the number 3. Okay? And supposedly, this is going to make the expression on the left equivalent to the expression on the right. Let's see. This is 4 times 3 is 12 minus 3. On the right, 14 times 3 is 42 plus 9, and then negative 2 times 3 is negative 6. I'll continue. Over here on the left, you had 5 times. Now 12 minus 3 is 9. And over here, 42 plus 9 is 51. 5 times 9 is 45, and 51 minus 6 is 45. Look at that. When I plug in 3, which is our answer, the expression on the left is equivalent to the expression on the right. So 3, x equal to 3, is indeed our one and only solution. And I verified it now. All right, check out this next example. We got 1/5 times 11x plus 9 equals to 4/3 times x plus 1 minus 2. Usually when I show students this example, they get a little nervous and they get a little intimidated by the fractions. Now, whenever I have an equation with fractions, most of the time I clear out the fractions. How do I do that? By multiplying each term by the LCD. So this is my tip. Eliminate the fractions. So you need to find the LCD, which is going to be the least common multiple of the denominators. Now watch this. Your denominators are 5 and 3. Let's list out the multiples of 5. 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15, 20, 25, 30, 35, and the list goes on and on and on. These are the multiples of 5. What are the multiples of 3? Well, 3 times 1, 3 times 2, which is 6, 3 times 3, which is 9, and then 12, 15, 18, 21, 24, and the list goes on and on. The least common multiple is the LCD. And you can see by comparing your lists that the least common multiple between 3 and 5 is 15. So therefore, the LCD in this problem is 15. So this is what I've done. I put a 15 next to each term in my equation. I'm multiplying every single term. Even if it doesn't have a fraction, I need to multiply it by 15 as well. Okay, so even that -2 on the end. So this is what I'm going to do. I'm going to cross cancel. So this is how this works. 5 divides into 15 3 times. 3 divides into 15 5 times. So really, what I have left here is 3 times 1. I have 5 times 4. Okay? So really, my equation turns out to be 3 times 11x plus 9 is equal to 20 times x plus 1 minus 30. 15 times 2. So look how much nicer my equation looks without the fractions. Hey, by the way, did you notice that I kept the terms inside the parentheses the same? So really, you're just multiplying the coefficient outside the parentheses by 15 and 4/3 by 15, okay? All right, now what comes next is you distributing the 3 and distributing the 20. And that would give you 33x plus 27 is equal to 20 times x plus 20 minus 30. Before you go and move any terms to the other side of the equation, please notice that these two terms are like terms. They're both constants, so you can combine them. So you get 33x plus 27 is equal to 20x minus 10. Okay, now this is the point at which I will collect all of my x's on one side. So I'm going to collect my variables on the left side of the equation. I'm going to do that by subtracting 20x from both sides, because subtraction is the opposite of addition. So these 20x's are gone, and we all know that 33x minus 20x is 13x. Bring down the minus 10. Now, if you're bringing your variables to the left like me, that means your constants have to go to the right. So the opposite of adding 27 is subtracting 27. Be very careful here. Negative 10 minus 27, that does not give you a positive. The only time you end up with the positive is when you are multiplying two negatives or dividing two negatives. Right here, we are adding two negatives. And when you add two negatives, your sum is still negative. All right? So don't make the assumption that two negatives always gives you a positive. That's not necessarily true. The only time two negatives give you a positive is when you're multiplying and you're dividing. So the left-hand side is 13x, just bring that down. And the right-hand side, when you have negative 10 and then you subtract 27, you're now at negative 37. Now the opposite of multiplying by 13 is dividing by 13. Okay? Of course, 13 divided by 13 is just 1. So you got 1 times x, which is just x, is equal to negative 37 thirteenths. That's your answer. This is called an improper fraction, and there's nothing inappropriate or wrong about an improper fraction as long as it's simplified. And this is simplified because 37 and 13 do not share any common factors because they're prime. So this is your final answer. You do not have to change this to a decimal. You do not have to change this to a mixed number. You're fine. So this is our solution. Check out this example. Example 3 says solve each equation. So there's going to be two different equations I want us to look at. Here's the first one, okay? Something interesting happens here when we solve this equation. All right, here we go. Let's distribute negative 3. Let's distribute. Now be careful here. You're distributing a negative 4. Remember, the sign in front of the term belongs to the term. Another thing that you want to be careful about is to follow the order of operations. Do not add negative 7 and negative 4 together. That would be out of order. The first thing you want to do is multiply, okay, by distributing. So you cannot add these two numbers. Another thing to be careful about, do not distribute negative 3 to the negative 5. You're only distributing negative 3 to the two terms that are inside the parentheses. Okay, So then this becomes what? Negative 3x minus 6 minus 5 is equal to x minus 7 minus 4x minus 4. Now let's combine like terms on both sides of this equation. So on the left-hand side, you have a pair of constant terms that you can combine. On the right, you have that variable term and this variable term that you can combine. And then you also have negative 7 and negative 4 that you can combine. So there's a lot of combining going on. On the left, it's negative 3x minus 11. And on the right, it's negative 3x minus 11. Notice that the left-hand side expression is exactly equal to the right-hand side expression. What that tells me right now is that no matter what I plug in for x, no matter what value I consider for the variable, this left-hand side will always be the same value as the right. Regardless of my input, this statement will be true. Here, let me go further here to maybe drive home my point. Maybe you want to bring all your variables to the left-hand side. You can do that by using addition, because addition is the opposite of subtraction. But what happens is negative 3x plus 3x is just 0. And so all you're left with is just negative 11 is equal to negative 11. Your variables canceled, and you're left with a true statement. Negative 11 is equal to negative 11, of course. This is a true statement. Okay? And whenever your variables disappear on you, whenever your variables cancel themselves out, and the statement you have as a result is a true statement, then your answer is all real numbers. What this means is no matter what you plug in for x in the original statement, no matter what number you plug in, this statement will always be satisfied. This equation will always be satisfied. That is to say, this statement will always be a true statement. Okay? Whenever you are solving an equation and your variables cancel, and you're left with a true statement like this, like negative 11 is equal to negative 11, or 7 is equal to 7, or 9 is equal to 9, or whatever have you, if your variables cancel and you're left with a true statement, your final answer is all real numbers. And what that means is this statement will be true regardless of what you plug in for the variable. That is to say, this statement is called an identity. An identity, by definition, is a statement that is always true. A statement that is always true is called an identity. And that's what this is. We didn't know it was an identity until we got to the end of the problem. And so now that we know that this statement will always be true, this equation will always be satisfied, your answer is all real numbers, we can describe this statement by calling it an identity. Awesome. Let's go to the next example. This next example says negative 0.5 times x plus 7 minus 0.2 is equal to 0.3x minus 0.8 times x plus 1. Now, a few examples ago, I showed you how to eliminate an equation of fractions. What did we do? We multiplied by the LCD. That's exactly what you're going to do here. Let me show you. Decimals are fractions. This decimal, negative 0.5, is the same thing as negative 5 over 10. This is negative 2 over 10. This is 3 over 10x. This is negative 8 over 10. Here, allow me to rewrite it like this for us. So decimals are fractions. In this case, the LCD is 10 because all the denominators are 10. 10 is going to be the least common multiple. So what we're going to do is we're going to, the same strategy, the same tip that I shared earlier, multiply every single term by the LCD, which in this case is 10. All right, so you can see that I've multiplied every single term by 10. Now you know what I'm going to do. I'm going to cross multiply. So then this 10 will divide out with this 10 for this 10, that 10 for that 10, that 10 for that 10. And so really, all you're left with then is negative 5 times x plus 7 minus 2 is equal to 3x minus 8 times x plus 1. Look at that. Now this equation no longer, I don't know if that looks like an x for us. Here, let me make that a little neater there. Okay, give me a second. There we go, better. This equation now no longer has any decimals, okay? So what we're gonna do now is solve this equation. What I would love to see you do is pause this video and solve this equation, and let's see if you and I agree at the end. So go ahead and pause the video, solve it on your own, and I'll check back in with you. Okay, so I hope you distributed -5. I hope you distributed a -8. That should have led you to -5x minus 35 minus 2 is equal to 3x minus 8x minus 8. Next, I hope you combine like terms. On the left-hand side, the like terms are -35 and -2. On the right-hand side, it's the -8x and the positive 3x that you're combining, which will lead you to -5x minus 37 is equal to -5x minus 8. What I hope you did next is move all your variables to one side. Now remember that it doesn't matter which side you move your variables to. I am going to move the variables to the left-hand side by using the opposite of subtraction, which is addition. I'm going to add 5x to both sides. We all know that -5x and positive 5x is 0x, so those are gone. So your variables just canceled out, and the statement that you're left with is -37 is equal to -8, which is not true. This is called a contradiction. That is to say, the statement is false. -37 is not equal to -8. Now, whenever your variables cancel themselves out, and you are left with a false statement, that means your final answer is no solution. So I'll say that one more time. Whenever your variables cancel out and you're left with a false statement, that means the final answer is no solution. And what that means is no matter what you plug in, where's the original equation? Here it is up here. There it is. The original equation is here, right? That means no matter what you plug in for x, it will not satisfy the equation. No matter what you plug in for x, this statement will always be false. This expression on the left will never have the same value as the expression on the right. I can describe this statement by calling it a contradiction. This statement can be described as a contradiction. Whenever your answer is no solution, which means that the variables canceled out and you're left with a false statement, you have a contradiction. Here's a little summary for your notes. Whenever the variables cancel and you're left with a true statement, your final answer is all real numbers. Whenever the variables cancel and you're left with a false statement, the answer is no solution. Now, if this happens, case number 1 here, that means the equation is an identity. Whenever this happens, case number 2, that means your equation is a contradiction. All right, everybody, so you can add this to your notes. So for this case here, you have an identity on your hands. For this case here, you have a contradiction on your hands.